So our last major section in Chapter 1 is to really start talking about some of the other important aspects of what goes on with bonding. And we're going to start that by looking specifically at polar covalent bonds. And polar covalent bonds will end up being the most important types of bonds that we have because most of the reactions that we learn about, and we're going to be learning about a lot of reactions over the next, few months. But most reactions that we learn about are initiated by the attraction of polar covalent bonds to each other. Most commonly, we see polar covalent bonds when the difference in electronegativity between two elements is between 0.3 and about 1.7. Now, you will sometimes see some other numbers cited here. You might see this as 0.5, and you might see this one as high as 2. But basically, we're looking for polar bonds. And a good example of that would be something that we see, such as, a carbon-fluorine bond, where the carbon has an electronegativity of 2.5 and the fluorine has an electronegativity of 4.0. And so that results in this molecule having a dipole from carbon to fluorine. And perhaps one of the most important examples is carbon-oxygen. So this type of species is something that we call a carbonyl, and that's a name that we'll learn more about in Chapter 3. But carbonyls are carbons double bonded to oxygen. And carbon being more electronegative than carbon, or oxygen being more electronegative than carbon, creates a dipole that goes towards the oxygen and leads to a lot of interesting reactivity for these types of molecules. It is also important to remember, though, that just because we have polar bonds within a molecule, such as this one, doesn't mean that the molecule has a dipole. The reason for that is you can see we have one dipole going towards bromine. We have a second dipole here going towards bromine, but they end up canceling out. So overall, this molecule has no net dipole. But as we'll see throughout this course, polar covalent bonds control a lot of reactivity within organic molecules. Now, overall, we use this term inductive effect to refer to what's going on here. So the inductive effect is the shifting of electrons in a bond. And this is based on differing electronegativities. Now, this doesn't just influence bonding and reactions. One of the most important things that this also affects is solubility. Solubility is based on similarity in polarity. And what we mean by that is if we have a polar solvent, such as water, and a polar solute, such as sodium hydroxide, those will be soluble in each other. If, on the other hand, though, we have a polar solvent such as water and a nonpolar solvent such as toluene, toluene being C7H8, they will not be soluble. And so if we want two things to be soluble, in general, we need similar polarities. So a nonpolar solute will be soluble in nonpolar solvents, whereas a polar solute will require a polar solvent in order to dissolve it. Alright, now I also want to review the calculation of formal charge. So this should be something we learned in general chemistry. But when we're drawing a Lewis structure, for example, this one, how do we know where to put the charges? So remember that formal charge is equal to the number of valence electrons minus 1/2 of the bonding electrons minus all of the non-bonding electrons. So let's start by looking at this carbon. Carbon, we know, has 4 valence electrons. How many bonding electrons does this carbon have? Well, this carbon has 4 bonds. Each bond is made up of 2 electrons. So this carbon has 8 bonding electrons. So we take that divided by 2. How many non-bonding electrons? Well, a non-bonding electron is another name for a lone pair. This carbon has no lone pairs, so we have 0 there. So 4 minus 8 over 2 minus 0 is equal to 0. So this carbon has a formal charge of 0. What about the oxygen? Well, oxygen has 6 valence electrons. Here, this oxygen only has 1 bond, so that's 2 bonding electrons over 2. It has 6 non-bonding electrons coming from 3 lone pairs, so we subtract 6 and we get a charge of -1. So in our Lewis structure here, we should have a negative charge on oxygen. What about sulfur? Sulfur normally has 6 valence electrons, but here the sulfur has 3 bonds, or 6 bonding electrons, and 1 lone pair for 2 electrons, which gives us +1, and so we put our plus formal charge on sulfur. So this brings us to our final topic in Chapter 1, which is resonance. And resonance is something that you probably learned a little bit about in general chemistry, but we're going to take resonance to a whole nother level in organic chemistry. And resonance is important in a lot of ways. When we get to spectroscopy in a couple weeks, we're going to see a lot of resonance, and then it's going to come into play in a lot of the reactions that we study in this course. So first of all, what do we mean by resonance? So what I'd like you to do is to pause the video in a moment and go ahead and draw the Lewis structure for the carbonate ion, CO3 2-. And come back and see what you get. All right, so most likely you came up with one of these structures. So which one is correct? Well, typically a carbon-oxygen single bond has a bond length of about 1.43 angstroms, while a carbon-oxygen double bond comes in at about 1.2 angstroms. But for carbonate, all three bonds are about 1.28 angstroms. So what that suggests to us is that all three bonds in carbonate are, first of all, the same, but they're also stronger than a single bond because the bond length is shorter, but they're weaker than a double bond because the bond length is longer. So what do we have going on here? Well, the reality is that all three of these structures represent carbonate. But in reality, none of them actually exist. And the true structure of carbonate is actually a hybrid of these three. And so we designate that with this kind of arrow. And note that's a double-headed arrow, which represents resonance. Don't get that confused with the two arrows like this, which represent equilibrium. And so very, very importantly, when we're dealing with resonance structures, as we are here for carbonate, the actual structure of carbonate is a hybrid of these three. We don't mean that these three structures are interconverting, because they're not. The three structures, the way we've drawn them here, don't actually exist. The true structure of carbonate lies somewhere in the middle. So each of the three bonds in carbonate is slightly stronger than a single bond, but not as strong as a double bond. And unfortunately, just because of the way we represent molecules on paper, we're limited and we can't draw a true structure for what carbonate looks like. So we represent it in this way. So how do we draw resonance structures? So what are the guidelines? First thing, and probably the most important, is only pi electrons and lone pairs can move. So you cannot break or form sigma bonds. Once you break a sigma bond, you've formed a sigma bond, you've made a new compound. All of the structures must be valid. And by that we mean valid Lewis structures. So you can't draw a resonance structure that has 5 bonds to carbon. It's not a valid Lewis structure, and it's still not a valid resonance structure. Now, resonance is a very, very stabilizing effect. And so what that means is that the actual energy of the molecule is lower than all of the drawn resonance structures. So anytime you can draw resonance structures for a molecule, That will help to stabilize the molecule. All right, the next one, let me go to a clean page. Not all resonance structures contribute equally. So while every resonance structure that we can draw does contribute to the overall picture of the molecule, they're not always going to be equal. For example, here's benzene. The first two structures that I'm drawing do contribute equally. They're of equal importance. But over here on the right is a valid resonance structure. All I've done is move the pi electrons, and I'll explain in a little bit how we go about doing that. But while that is a valid resonance structure, it's not nearly as important as the first ones that we drew. So how do we evaluate what resonance structures are more important than others? So first of all, more bonds is better. So in this molecule, we can take the pi electrons and move them up onto the oxygen. But that's done two things. It's given us less bonds, so that makes it a worse resonance structure. And in addition, less charges are also better. So we've added more charges to it. Structures where all atoms have an octet are more favorable. And we can also say that charge separation decreases stability. So the following are, again, resonance structures of each other. But you notice the structure on the left has the two charges far away from each other, while on the right, they're right next to each other. That means that this is a more important, more stable resonance structure. And so does that mean that the structure on the right will be a larger contributor to the overall structure of the molecule? The answer is yes. All right, so how do we draw resonance structures? So when you did this in general chemistry, these were probably fairly simple molecules, and you just approached them like you'd approach any other Lewis structure. But here, our molecules are going to get more complicated than anything we did in general chemistry. And so we're going to need to have a way that lets us do this that's a little more straightforward and lets us go from one structure to another more easily. So today, this here is going to be the first time that we refer to our curved arrow notation. Curved arrow notation is a way that within structures or within reactions, we can follow the flow of electrons. And we typically use two types of arrows. This very normal looking arrow, and then this, which we call a fishhook arrow. The difference in these arrows is the number of electrons that they represent. The structure on the left, or the arrow on the left, represents a movement of 2 electrons, while the arrow on the right represents a movement of 1 electron. All right, so let's look at an example and see how this works. So here's acetone. Can we draw a resonance structure for acetone? Well, in order to draw a resonance structure, what are we able to move? So again, we can move lone pairs, and we can move pi bonds. So let's start with lone pairs. Where do we have lone pairs in this molecule that we could try and move? Well, on the oxygen. Where can they go? Well, they can't go to this carbon or to this carbon or any of the hydrogens because that would create a new sigma bond. And once we create new sigma bonds, we're not dealing with resonance anymore. So we can try moving them to the carbon that they're already attached to. The problem with doing that, though, is that would now give our carbon here 5 bonds. And we know that carbon can never have 5 bonds. Now, if the carbon could then give up some of its electrons somewhere else, this would be okay. But that carbon only has sigma bonds other than being bonded to the oxygen. And so there's nothing we can do there. So that doesn't work. So what's our other alternative? Well, we could move the electrons in the pi bond. Now, which way should we move them? Should we move them to the carbon or to the oxygen? Well, it turns out it makes the most sense to move them to the oxygen because the oxygen is the more electronegative element here. So we take our arrow and draw it like this. What this arrow is showing us is where the arrow starts is with the pi electrons. So that shows us the pi electrons are moving. The end of the arrow is where they're going. So those electrons are going on to oxygen. So what this looks like now is this. We've taken one of the pi electrons between carbon and oxygen and made them into a lone pair on oxygen. Now, because we've moved electrons around, we need to add in the formal charges. So you may want to stop for a minute here and calculate those. But another way to think about it is we've removed electrons from carbon. Therefore, that carbon doesn't have enough electrons anymore. It's going to be positive, and the oxygen has gained electrons. It's going to be negative. But notice that we started with a neutral molecule, and if we add up all of the charges within our resonance structure, we still have a neutral molecule. And that should always be the case for resonance. All right, let's do another example. Now, where should we start here? Well, we can see very similar to the above example, we have a carbon-oxygen double bond. And so we were able to draw a resonance structure by doing that last time. And we can do that same thing again. But now that cation that we formed on carbon is positively charged. But it's also next to an atom, nitrogen, that has a lone pair. So what could we do with this lone pair? Well, if we add this lone pair in here towards the carbon, we know that that didn't work last time. But this time we're dealing with a carbon that only has 6 electrons. And so that carbon is able to accept those electrons from nitrogen and form another resonance structure. Such as the one we've pictured here. All right, let's do one more. So you may already be noticing by now that carbonyls are a very common thing to have with resonance structures. And that's something you should start to see throughout this course and organic 2. There's a lot of patterns, a lot of similarities, a lot of things that repeat themselves from one to the next to the next. So we can do the same thing we've done here and move our pi electrons onto oxygen. And now we have a carbocation which is next to another pi bond. So can that pi bond shift its electrons over towards the cation to make a new resonance structure? In fact, it can. As a result, this carbon here has given up electrons and it is going to be positively charged. So overall, what we're looking for in these types of situations is how we move electrons. We can move only pi electrons and lone pairs. It's always easy to move electrons to carbocations, or cations in general, but usually carbocations. And anions are usually going to be willing to give up electrons. So at this point, you should get out in-class exercise number 4, which deals with practice for drawing resonance structures, and try drawing some resonance structures for each of the molecules that are given. Again, I want to emphasize just how important this idea of resonance is. This is something we're going to see, in every single chapter we cover for the rest of the course. So make sure you get a good grasp on resonance right now. Do as much practice as you can. And in the next video, we will go through some of those practice examples.